Thank you. Then I will not repeat.
So,
Yeah.
what I discussed last time was some sketchy view of group theory. I tried my best to avoid the technical details and gave you the major points. What we discussed was group theory and how the Anglo-momentum algebra actually is nothing but description of rotation group, and finally it leads to spin group, SU2 group, when we have a matrix treatment of Anglo-momentum algebra. I suppose we all in MSc class we have done these things, and basically it is commutation and relation of the generators, which are operators here, Anglo-momentum operators. They act as the generator of rotation. So following that, we continue. So then I introduce how degeneracy can be understood as a consequence of some symmetric group of, say, hydrogen atom. But also there are terms which break the degeneracy because of relativistic correction and the fine structure caused by LS coupling. And also the degeneracy may be broken because of external fields like magnetic field or Stark, the external electric field. So we all know Stark effect and Zeeman effect. So with that, I ended up with some understanding of SU2 group, special unitary group in two dimension describing spin, which was simply taken over as a isospin symmetry. As far as the mathematics is concerned, SU2 spin or SU2 isospin, there may be other kind of SU2 groups we will come across in particle physics. So their mathematical structure remains the same. That is the beauty. And though of course they at different times they will be representing different physical concepts. And those who are new to SU2 terminology, they shouldn't really be afraid of it because it is nothing but rotation in complex vector spaces. So here in SU2 case, we have two-dimensional complex vectors and you rotate them. And in that case, we have the group formed by rotation in that space. So now in this today's talk, I will go from SU2 to SU3 and how it was used to understand hadronic classification. And I hope I will have time to go to quark model and other things. Otherwise, we will continue. So just as a quick reminder, what we found was there are several hundreds of the hadrons, baryons, and mesons carrying spin half to 15 by 2 have been observed. Similarly, mesons with spin up to 4 and so they are there. Obviously, they are not fundamental. Most of them decay. So probably they like to go to the ground state. So ground state of baryon, you may treat spin half, baryon and mesons spin 0. So both baryon spin half and meson spin 0 preferably decay, or they can't decay through strong interaction. So they decay through weak and electromagnetic interaction. And what we also noticed that this baryon and meson seem to appear in a grouping of 8 or 10 octet and decouplets. Then the near degeneracy of these particles belonging to one isomultiplet or even bigger octet group, octet multiplet, seem to indicate presence of some kind of internal symmetry, and we learned that how symmetries lead to degeneracy and also the conservation law. As a quick reminder, especially for those who probably may not be there, group theory is nothing but it is a description of a set of elements which form a group, which can be combined with some operation. It could be anything like addition, multiplication, or some other thing, which satisfy these four postulates: closure, associativity, identity, inverse. I'm sure everybody must have learned these things in school from NCERT math at 5th, 6th, 7th class level. So I won't go into the detail of this, But main idea is that rotations, once we realize that the rotations form a group, what do? We look for the generator of the, I mean, these transformation, and these come out to be orbital angular momentum operators. So they act as the generator of rotation. This I also left as a exercise to show. And then we construct commutation relation with the help of R and P operator, because L is nothing but cross product of R and P. And then we understand that commutator between say Lx and Ly, that is Lx Ly minus Ly Lx, can be expressed as a linear combination of the operators themselves. And then we find, since all of them don't commute, therefore they cannot be diagonalized. It means all of them cannot act as an eigenoperator. We can have eigenoperator which must actually commute with, with each other. Therefore, only one of them, and conventionally we choose third component of orbital angular momentum to be the eigenoperator. The other two we have seen they form raising and lowering or shift operators. So L3 is used as an eigenoperator. Then we also find that a sum of their squares, Lx square plus Ly square plus L square, this is a new class of operator, which is in group theoretical language we call them Casimir operator. The beauty of this Casimir operator is they commute with all the operators which we have started with. So that is the point, that we can use these two L3 and L square kind of operators as eigenoperators, and their eigenvalues, say L and M, all of us know that L square has eigenvalues L into L plus 1 H square, etc. And that L we are using and M as the eigenvalue of L3 to designate the state. And composition of state is actually not a new thing. All of us have learned helium atom, where we know that two spin half particles can be combined together to generate spin 1 and spin 0 states, and spin 1 can be expressed as a combination of up, down, down, up, down states. Coefficients which appear in that are an example of CG coefficient which we use generally, and these CG coefficients ultimately are used in Wigner-Riccard theorem for applying perturbation theory to different problems. So again, then as a quick reminder, some of the Behrend emissions, as we see, are nearly mass degenerate, and Heisenberg in as early as 1932, recognizing the almost near equality of proton and neutron mass, suggested the idea of isospin symmetry. Iso simply means something similar. So this way, this proton and neutron can be represented by the two component column matrix. We call them spanners. And this is very similar to ordinary spin up and spin down state of an electron for SU2 group, that is SU2 spin group. And we have also learned yesterday that these states 1 0 and 0 1 spin up and spin down states are by the poly exactly following that mathematical spin up treat 1 0 and 0 1 as the spin isospin half state on which poly-like matrices, but we prefer matrices for the case of isospin, but mathematically they are exactly the same. We want to enlarge the symmetry. That means we combine isospin with ordinary spin. So therefore we will need same matrices at two places. So it is better to use a different symbols. So sigma matrices are the standard poly matrices, and the same matrices we name as tau matrices, which act as the generator of isospin transformations. I hope everybody is following, but your questions are always welcome. So mathematically, as we have been talking about, isospin has exactly the same commutation relation, exactly the same mathematical treatment as the spin. The only change I have done is I want to bring the concept of this particular quantity. What I am saying here is that commutation relation of isospin operators I, Ij are given by as a linear combination of I. There is a sum over k here understood. So this kind of a thing, which I suppose everybody knows, Levi-Spitzer symbol. This is one when ijk are in 1, 2, 3 values, or they are even permutation. Otherwise -1, and it is these are 0 if they are any of the two indices are equal. So that way, the fundamental representation or multiplied will be isospin up and isospin down. So this is just a shorthand symbol for these two things. And if you want to generate higher representation exactly like spin, we have here isospin 0, that means isoscalar, isospin half, isospinors, isovector, isospin 1, isoquadrat, 3 by 2, and so on. So in that way, just to give you immediate example, when spine were proposed by Yakova in 1935, they could easily be accommodated in this isospin framework. So 3 points are which are nearly the same mass, giving us more confidence in our isospin symmetry treatment. They can be represented as a 3-component column vector, exactly like proton and neutron forming isodoublet. So besides the nucleons and pions, around 1950s and after that, many mesons and baryons have been found to form isospin multiplet, and particles belonging to one isospin multiplet, they have approximately same mass. So here I am giving you the table again, but no, put slightly differently. So we have, this is the story again, I actually remind you before 1965 or so. Example of such hadron isomultiplets, even carrying new quantum numbers like charm and bottom and so on so forth. But keeping the life simple, let me show you that how mesons with spin 0, parity minus, superscalar particle, and mesons, these are vector mesons carrying spin 1 and parity minus, spin parity half plus, and also 3 by 2 plus. If you like, you can call it low-lying mesons and baryon. Of course, other particles are also there. They also form a similar kind of a structure. So whatever we are seeing here, that is essentially duplicated when we go to high spin hadrons. But the point which you can note here is that we have isospin half, which originally was started with the proton and neutron approximate degeneracy. We find there are many more like mesons, for example, K plus K0, which form isospinner with the third component plus half and minus half, and they carry 498, and which is quite close. And then in vector mesons, we have their heavy brothers, K star plus and K star 0 with mass around 892, 896. So these are nearly linear degenerate. So is the case with this. By the way, there is another way of calling these hadrons which we have picked up. That is S wave hadron. This is just a name. Explain some other time. If I restrict this, I have isodoublet. another isodoublet also, that is K0 bar and K minus. K minus is antiparticle of K plus. K0 bar is antiparticle of K0. This is the typical property of an elementary particle, that for every particle we have antiparticle, or sometimes a particle may itself be its own antiparticle. For example, pi zero, eta, eta prime. Then what is the distinction between these? Will probably remember strangeness which was required behavior of these new particle produced, because the nucleons and pions are called unflavored or normal particle. All other particle which we are seeing here, they carry new quantum number like strangeness. And when you combine strangeness with Barer number, we call it hypercharge. So in hypercharge of K plus is +1 and -1. So the value of this doublet, because a Barer number for meson is obviously 0. Then we have isovector, and then also isoscalar, that is isospin 0, eta and eta prime states. So these, what we are seeing here, are different isomultiplets. Later on, we will put all these 8-9 particles in one bigger multiplet, which will require or indicate the presence of a high symmetry, that is SU3. We are restricting to SU2 isospin multiplets. So exactly similar to that, when we go to vector meson, we have iso doublet of K star plus and their antipartners. And then similar to pi, we have vector mesons rho plus, rho zero, rho minus, which form isovector. And also omega and pi, which form isoscalar. Were already seen around 65. Coming to the family of baryon, forming isodoublet is formed by cascade particle, also known as Xi particle. They carry charge Xi 0, neutral, and Xi minus. With mass around 1315 and 1326, not bad. Difference of 6 MeV among 1300 is not much. And then we also have iso 0 sigma mass around 1193, 97, again quite our faith in the isospin symmetry. Lambda comes out to be isosinglet. If you count them, you have 8 here, also 8 here, and also 8 here. Then as far as spin 3/2 plus particles are concerned, we have isodoublet, Xi star 0, Xi star minus. If you call them, you can call them to them to be heavy brother of these. In the same way, we have sigma star plus and sigma star 0 with mass close to each other. Then in case of having new, we have here a quadrant where we first example of iso quadrant is this, where we have W plus delta 0, delta minus, mass around the same thing. So in this way, these 2 plus 3 plus 5, 9 particle can. So we have to missing around 92. Right in SO3 symmetry. The existence of estimated the mass quite close to this on the basis of SO3 symmetry. So I hope everybody is convinced that we have mesons and baryons. We have formed very reliable degenerate mass. And interaction further of isospin, only the in fact now strong interactions take place at the quark level. And we have a quantum field theory, I mean, relativistic quantum field theory, quite analogous to quantum field theory of electromagnetic force, which are being applied on, on the study of quark physics, that is, how strong interaction takes at the quark level. But in those days, and actually speaking, even today, we understand short distances, but we understand really well this at the Fermi scale. That is called hadronization scale, at the scale which, or you can call it, is the size of the hadrons. The reason being, a strong coupling constant becomes very large, and the best tool which we have is perturbation theory. It starts breaking down. So, and as you know, the situation in nuclear physics, we have models. We don't have a theory of formation of nuclei, whereas in contrast to that, when we were studying hydrogen atom or all the other kind of atom and even their molecules, we are well sure that their dynamics is controlled by electromagnetic interaction, and one can use perturbation theory and all that to, 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 to understand. So in that situation, and especially in those days when we have hardly any understanding of strong interaction at nuclear scale or hadronic scale, these symmetries paved us a very good way. They showed us, even in the absence of dynamics, with knowledge of the strong interaction dynamics, we can exploit isospin symmetries and even other symmetries to relate at least various properties of these actually hadrons. So that was the beauty. Even without knowing the exact nature of strong interaction, we are able to exploit isospin symmetry, and it's it's breaking to make lots of prediction which actually come out to be all right. So first of all, we see that strong interaction obey isospin conservation law. So therefore, they obviously lead to mass degeneracy of members of an ultimate isomultiplet, which are mutually connected with isospin raising and lowering of the lowering operator, exactly the same way as we have seen. Yesterday, that how um, shift operator L plus L minus, and similarly shift operator S plus and S minus for spin relate or connect various various members of the same multiplet. So in that way, strong interaction will give equal mass contribution to all the members of an isomultiplet. So the small mass difference among the members of the one fixed isomultiplet is attributed to isospin breaking part of the Hamiltonian. And it's an interesting thing to have a connection with what we have understood yesterday. You know that hydrogen atom, in the beginning we find owner sp2 symmetry, that is spin symmetry. So electron spin up and spin down, they are supposed to be degenerate. But when you switch on the magnetic field, that is, it will cause Zeeman kind of a subjetting. I hope everybody remember here that essentially the term which is appearing in the Hamiltonian is nothing but mu dot B. Mu is the magnetic moment of the electron, and B is the external magnetic field. So if we choose B to be along that direction, then only the third component of isospin, spin will come, or the magnetic moment will come. And you know that magnetic moment is essentially given by E over 2mc into the spin operator. So in this way, the the presence of a magnetic field introduce a term in the potential which is involving S3 component of this spin. So, and you know that S3 component do not commute with all the generators of spin symmetry. Therefore, it will break the symmetry. Exactly in the same way, this small mass difference can be attributed to isospin breaking Hamiltonian. What does it mean? It means it has to be proportional to some component of isospin, say isos I3. And one can also understand this is essentially caused by electromagnetic interaction due to difference in their electric charge. I hope we remember here the Gell-Mann-Nishijima formula, which actually relate charge of a particle, charge of a hadron with the third component of isospin, that is Q equal I3 plus B plus S over 2. So in this way, the Hamiltonian responsible for hadron seems to have two parts. One is the strong interaction part, which is isospin invariant. Plus, there is a small contribution coming from electromagnetic force, that is isospin breaking, and this becomes proportional to charge, or you can say technically I3 component, because charge and I3 are basically connected. So this will give you the mass operator, that is m equal a plus b cube. We don't know a, we don't know b, because we will know a and b only if we have a proper theory of strong interaction. So pretending that we don't know, even if we know a bit now. So what do we do? So we find that mass of a isomultiplet will be expressible in terms of just two uh, unknown constants. So I can leave this as an exercise for my young friends to show that simply you write down mass of sigma plus sigma minus and sigma zero coming from A plus B. You can guess from for sigma plus it is going to be A plus B. For sigma minus it would be A minus B, and for sigma zero it is going to be only A. So this is how we immediately reach at a interesting interesting relation that that gives us a kind of formula for masses of sigma baryon, and obviously this works very well. Exactly the same kind of a formula can be obtained for a spin 3 by 2 baryons. It will not be of much use for iso doublet because we have two inputs and two constants. So at least here we are seeing it. In fact, isospin symmetry has much more power and we can exploit it. I will talk about these things in much more detail actually later on when we will be talking about forces. I hope Professor Shastri will give me that opportunity. But at this moment, what I'm saying is that isospin has a capacity, has a power to relate excuse me, decay rates of various hadron decays. The only constraint is that initial particle which is decaying and final state particle should belong to same isomultiplet. For example, I have chosen here some of the decays. There are many kind of decays and many more decays if you look at particle data group. But just to illustrate, and as I have been okay, let me spend a bit minute on this sheet. These are heavy states, so they will decay to this one with the emission of ion. You can easily see that they have sufficient mass difference to emit a ion, and same is true of this delta. These delta state can go to nucleon state with along with the emission of ion. In fact, this K star can also decay to K and pi and various other things. But I will talk about these decays in quite later on. So here I have chosen that for all the kind of decays, because all these three interactions, strong interaction, electromagnetic interaction, and weak weak interaction, they can cause particles to they can cause particle to decay. They obey certain conservation law, even if they are violating certain conservation law for the case of weak decay. They do it in some special manner. So that is what we will see later on. But choosing as examples here, so you see that in out of the six strong decays, the initial state particle belong to one isomultiplet, and all of them are going to proton or nucleons and pi. So this way, the final state baryon and meson also form isomultiplet. So all these six decays can be related just with the help of isospin symmetry. And since these are strong interaction, so they honor isospin symmetry. Technically, we will call that their operator responsible for strong interaction is going to be isospin scalar. So it is not much of a problem. You have to just apply the combination rule of isospin half and isospin 1 to generate isospin 3 by 2. So those who have learned CG coefficient in the case of angular momentum, it is for them a trivial exercise to to express these six uh, decay amplitude in just one unknown parameter. So they will get related, and we use Fermi golden rule to express their decay rate in terms of their decay amplitude scale. It is going to be a little bit actually technical now. I will don't go in the detail of all this, but I will talk about these things later on. These are nice application of isospin symmetries. Similarly, for electromagnetic decays, we have vector mesons which are decaying to pseudoscalar meson with the emission of photon. So such processes where rho plus is decaying to pi plus, or rho zero is decaying to pi zero, or rho minus is decaying to pi minus. So you find here that rho plus, rho zero, rho pi, rho minus form one isomultiplet, and then pi plus, pi zero, pi minus in the final state they form one isobacter. So these three can be related through isospin symmetry. In the same way, k star plus going to k plus gamma, and k star zero going to k zero gamma, because here again initial state and final state respectively belong to same isomultiplet. So they can be related. But on weak decays, see, we have many examples which I have chosen here. Sigma going to nucleon and pi. There are three observed decay where sigma plus is decaying to p and pi zero. Sigma plus is can also decay to neutron and pi plus, and sigma minus decay to nuclear this neutron and and pi minus. Since here again sigma plus sigma minus belong to the same isomultiplet, and proton neutron also belong to one isomultiplet, so one can exploit isospin symmetry to relate them. In the same way, lambda particle, this is the lightest strange part, baryon, is decaying to proton or pi minus, or it can also decay to neutron and pi zero, so they can be related. And finally, xi zero particle decaying to lambda pi zero, and xi zero particle can also go to, sorry, it should be minus here. Xi minus is decaying to lambda and pi minus, sorry for this typo. So those two can also be related. So this is the power of isospin symmetry. Not only it is showing you that there is a hidden symmetry responsible for a near degeneracy of various particles forming these isomultiplet, but it can also relate their mass even if their mass difference is there. So it breaks in a special way which can be understood. Not only that, it can also relate other properties like strong decays, electromagnetic decay, weak decays. So in those days when nothing much was known about strong interaction, they actually gave us quite a good relief. Even now, at present, they are respectable. So with this, now as we have seen that these particle, all of them carry same spin and same parity. Exactly is the same situation here. So these particle 8, 8, 8, and 9 or 10, they belong to the same, they carry same spin, same parity. So this indicate probably isospin spectrum needs to be enhanced. So earlier that if I3 along, Y along, again I remind you that along the Arion and Mesons, they are very nice symmetrical patterns which require some some understanding. And Gell-Mann and actually Niemann was Israeli. They actually realized that probably there is another layer of asymmetry. And since SU2 worked very well, actually, if you look at historical papers, people tried a different kind of group. But Gell-Mann and Niemann were the right group. That is special three dimension mere. So whatever we have thing for as of group theory, I have targeted. SU theory is nothing but a group which is generated by set of 3x3 unitarity matrices with unit determinant. This scheme was called eightfold way. The name was inspired. Actually, Gell-Mann was interested in Buddha's eightfold path, so he took this name from there. Because when you deal with particle, you find the mesons form octet. So he just called it SU3 eightfold way. It nicely explained the regularities of hydrospectra. That is what we'll see soon. So now a little bit of, as I mentioned, that SU3 group is nothing but a group of special unitary 3x3 matrices. Unitarity condition, suppose you chose a matrix and you find its inverse is nothing but its adjoint. That means complex conjugate with with transposition. So that condition, and they have determined. So that is what stand for. It means these unit this specify. So they can be to generate transformation. Remind you of we come across these kind of transformation several places in quantum physics. These are essentially nothing but rotations in complex dimensional vector space, complex vector spaces. So SU3 is essentially a group of rotations of complex vectors which live in three-dimensional complex vectors. As simple as that. So once we can think of because these rotations are more technically SU3 symmetry transformation. They preserve the length of the three complex vector. Three means three component complex vector. But interestingly here, how many generators you require? In fact, I can give you a general formula. If you are dealing with SUN groups, then number of generators that are required to be n square minus 1. In fact, this can be taken as a home exercise to see, because unitarity condition and determinant one condition will tell you so. And just compare it with SU2. There we have 2, so 2 square minus 1 is 3, so that is understandable. But what about orthogonal groups? Orthogonal groups require n into n minus 1 over 2 number of generators for SON or in general ON groups. So here, going with that, at mathematics, 3 square minus 1 is 8. So what we require is 8. In fact, when we will be talking about color, we will come across this S3 group again. But at that time, it will be representing colors, not the quarks. So we will see later on. But I can just try to give link for some enthusiastic people. So let those generators be TA, and they are usually expressed by 2, where lambdas are matrices. I hope you remember that spin operators were actually written down as half H sigma, where sigma were the Pauli matrices. So this half is being carried from that. So these are the eight generators, which are called Gell-Mann matrices. And those who are smart can immediately see that first three are nothing but polymetric 0, 1, 1, 0, 0 minus iota, iota 0, 1, 0, 0, 0 minus 1. These 2 cross 2 matrices were sigma 1, sigma 2, sigma 3. We have simply added a third row and third column of zeros. So once you allow them, what is so special about third place? We can have them second row and second column also two with zeros, which we can obtain from a sigma. So it is not a difficult exercise. You play with the sigma matrices by adding rows and column of zero, either at third place or second place or first place. You will end up with nine, nine 3 cross 3 matrices, which will act as a generator of three things. In fact, this may remind you that it has something similarity with how do you develop a rotation in a three-dimensional space, a real vector space. We perform three successive uh, rotation about z-axis, y-axis, and x-axis. So 2 by 2 matrices which we use for describing rotation in two-dimensional space can be exploited in different ways to have overall three-dimensional rotations. So exactly the same thing is being done here also. If I hope you can see, but I want you to see many more things. That is, see that here it is. Operator is 1 1 minus 2. That is that is lambda 8. So they lambda 1, lambda 2, lambda 4, lambda 5, lambda 6, lambda 7. They have off diagonal elements non non-zero. So I again remind you that these diagonal operators like sigma 3, they are essentially the eigen operator. So lambda 3 and lambda 8 will act as eigenoperator, and the remaining 6, lambda 1 actually, lambda 2, lambda 4, lambda 5, and lambda 6, lambda 7, they will develop three sets of shift operators. For example, if you restrict to this place, it is something like I3, and lambda 1 and lambda 2 are I1 and I2, and their plus minus combination will change isospin. A similar kind of structure can be obtained here also. So one can have some meaning coming out of these Gell-Mann matrices. So as I mentioned, whenever we have a group, what do we do? Something is wrong. Anyhow, it doesn't matter. So as I said, that once we start with some transformation, we find the generators, and once we have the generator, we find all possible commutation relation among them. So here the commutation relation between these eight generators, which are given by lambda matrices, it is not a very big exercise to show that the commutator of TATV, that means TATV minus TBTV, TATVTA, can be expressed as a linear combination of these. So interestingly, these FBAC, which are analogous to epsilon ijk coming for isospin, are non-zero values are carrying only by these F's. So you can pick up ABC from here, or their permutations. So all other which are not connected with this are actually zero. So these structure constants, these are technically called structure constants. In fact, they carry the key of a group. So ultimately, the structure constant, but I will not go into the detail of that, are responsible to give you CG coefficient required for combination of states. So these generators, but I have already told you, they are third and eighth matrices. Only two are the diagonal, so they act as so it is so sorry for the typo. These act as the eigen operator, giving eigenvalues I3 and y. So that is the beauty. So the hypercharge y is coming as an eigenvalue of lambda 8, this matrix, and I3 will be coming from here. And remaining 6 will form 3 sets of shift operator, which will connect different states in a particular SU3 multiplet. Now again, recall that dimension of a multiplet. How did we obtain? We obtain it as 12 plus 1 for orbital angular momentum algebra, and 2s plus 1 for spin algebra, or 2i plus 1 for isospin algebra. So in that way, what we learned that dimension of a multiplet is decided by eigenvalues of the Casimir operator, that is L square kind of operator. Exactly here also, we will be able to have two Casimir operators, but I am avoiding these technical details. If some other time I will be talking about, I may give you the esoteric details of this kind of things. So the eigenvalues of, just trust me for the moment, the eigenvalues of Casimir operator, which is essentially constructed out of sum of squares of this and sum of cubes of this. With that will give you the dimensionality of the multiplet. Please remind yourself that for spin and for isospin, all dimensions were actually permitted, because we have isoscalar 1, isodoublet, isotriplet, isoquartet. So the dimensionality of multiplets are just the counter number 1, 2, 3, 4, 5. But when we come to SU3, not all actually values are permitted, and we have here singlet, triplet, anti-triplet, sextet, anti-sextet, octet, and 10. Then what is the beauty? Beauty is that those octet and decuplet pattern which we were seeing for the case of mesons and actually baryons, that is naturally coming as a consequence of SU3 symmetry. And states belonging to these uh, multiplets 8 and 10, or others also, can be designated with I3 and Y. I3 and Y are basically of third and eighth matrices. No, already I. Important, because when you are dealing with a group, you have to remember which subgroup chain you have really followed. Because we extended the SU2 isospin group to SU3 group, so that way the quantum numbers carried by isospin group are simply borrowed, carried further in this analysis. So do we have an alternative? That's an interesting thing. Yes, we can start with a SO3 group and then go to SO3 group. So the way we are generating higher group matters quite a lot. So not only the I3 and Y as the operator, but we also need to include I square operator, which will give you I into I plus 1 as the eigenvalue. So we need three set of three quantum number to actually designate the state. And this brings us to a particular interesting pattern. How these SU3 multiplet have SU2 content. So when we break SU3 to SU2, we will see the isomultiplet structure of SU3 three multiplets. So here again, I remind you y is nothing but hypercharge of A plus A. It is the eigenvalue of its generator, and these are iso2 isospin multiplet. So it is pure mathematics. If you go with the mathematics, you find not only we have octet of mesons and baryons, we also the group is so accurate and so powerful. This naturally tells you that this octet is not arbitrary octet. It is composed of four isomultiplets. That is one doublet, one triplet, and one singlet, and a doublet carrying different eigenvalues for the hypercharge 1, 0, minus 1 respectively. And this happens to be the case when we look at octet mesons and octet baryons. Whereas decoupled part is concerned, this is made up of isoquartet, isovector, isodoublet with a respective hypercharge value 1, 0, minus 1, minus 2, and that is filled by 3 by 2 plus baryons. So one can see that we have a isodoublet, we have isovector, we have isosinglet, and we have a isodoublet. So this perfectly match with this. And same is followed by vector motion. So that is why we trust SU3 symmetry, because it is giving you nice filling of the particle with exact description of their isospin degree of freedom. This table I have discussed many times. I will jump over this. Same thing you see here, that octets are filled by isodoublet, isosinglet, isotriplet, and isodoublet again. Exactly this pattern which we are seeing here. But when you come to 3 by 2 plus baryon, we have a quartet. We have sigma star and xi zero particle again 4, 3, 2, and 1. Actually, this is the interesting thing to note historically. When Gelman used SU3 simply to understand the hadron classification, at that time omega minus was not actually observed. This is just to remind you. I will come back to that point soon. If you plot I3 and Y plot, we have this kind of interesting diagram. I've already talked about this before, but when decouplet was formed, we find that in 1965 only nine particle, 4 delta, 3 sigma, and these were there. This was missing. So SU3 had the power to predict that there should be this vertex of this a triangle which should carry minus charge, because all particle along this row, along this diagonal, along this side carry the same charge. You see, interestingly, particle along this direction carry the same charge. So a sign of omega could be obtained. Not only that, Gelman could predict the mass of the omega exactly at the place. So that again shows you that we were on the right track. So SU3 made interesting predictions. That means it could explain octet, singlet, decuplet, multiplet structures, which is followed by spin 0, spin 1, and half plus and 3 by 2 barium. And as I mentioned, that following decuplet, because 9 could not be fit in the octet, so we have to go for the next representation, that is 10. So omega was missing, and in 1964 he actually predicted, and within a year or so this was observed exactly at the right place. We have already seen how do we understand masses in isospin spectrum. Same approach is used here, but obviously trusting SU2 was quite good, because particles belonging to isospin multiplet are quite close, but all these particles don't have a common mass, so their mass difference is quite large. So this brings us to a understanding that as far as strong interactions are concerned, they do honor SU2 symmetry, that is isospin symmetry. But as far as SU3 symmetry is concerned, a strong interaction actually don't obey them totally. So they have two parts in the Hamiltonian describing strong forces. One is SU3 symmetry, and second is SU3 breaking. This is going little technical at this point, but I can only help you to say that SU3 breaking somehow behaves like a term which is proportional to lambda 8. So anyway, with this kind of a understanding, Gell-Mann and Kubo was at Rochester University, Gell-Mann at Caltech. They could obtain independently mass formula which relate nucleon, xi, lambda and sigma mass in this particular way, and agreement is quite, quite actually reliable. So that shows that SU3, even without knowing the strong interaction dynamics, have power to relate the various observations. A similar formula can also be obtained for that is k, pi, and eta kind of a thing. But that probably you can follow the book, or maybe at some other time I can give you that. In fact, things did not stop here. Once people actually realize that we are going in the right direction when we are discovering internal symmetries of the hadron, then people exploited these asymmetries to make particle. So now the power was bigger because SU3 symmetry can even actually relate different decays where different isospin multiplets are appearing in the final state and initial state. In fact, once we were encouraged by the accuracy of the predictions, people enlarged the SU3 group to SU4, SU5, SU6 group in order to understand hadronic classification of a new particle, which we will see later. But not only that, they enlarged the group along the internal direction. They even try to compare this flavor symmetry with the spin symmetry. So SU2 group of spin was used, and SU3 for flavor was used, and these combined together, they were put in a bigger group that is SU6. This SU6 could even make very interesting predictions about say the say the ratio of magnetic moments. The magnetic moment is 2.793, and Newton magnetic moment is minus 1.913. So the ratio comes up to be minus 1.46 experimentally, and theoretically, SO6 could even give you the prediction that their ratio should be minus 3/2. Quite nice. So maybe can I stop here or go further? Hello, hello.
So we can stop here
Yes, sir.
soon.
I think we can stop here. I will just talk about a small sheet here and then go further, because we have seen that SU3 allows many other kind of actual multiplet, that is 3 star, 6 and 6 star. So even though it nicely explained octet and decuplet pattern followed by meson and baryon, but this question was raised. What about these lower dimension multiplet, that is 3 star, 6 star? So in fact, that ultimately led us to a understanding of another layer of the onion, that because when you answer some question, you end up new questions. So why nature realizes only 1, 8, and 10 representation for the hadron, whereas SU3 does actually possess low representation like 3 star, 6 star. So to understand this thing further, around 1964, Gell-Mann and Zweig independently suggested probably these hadrons are made of new kind of particle called quarks, and baryons with 3 quarks, and mesons are formed as a bound state of quark antiquarks. Like proton is made up of 2u quark and d quark, and neutron is made up of 1u and 2d quarks, and similarly mesons. So in this way, these 3 kind of quarks downstream can be used to fill up the triplet representation, and antiquark are filled up by the 3, and diquark states are used to fill up 6 stars and all that. I will continue with this shit tomorrow. Thank you very much.
Thank you, sir. Thank you so much. Thank you very much, sir.
So now I can switch
Okay.
off, Alexa.
Yes, thank you very much.